Really appreciate you all joining our webinar, Beyond Mass Concentration, the Synergy of Black Carbon and Particulate Matter Measurements in Air Quality Monitoring. Really honored today to have you all. This is a super exciting discussion, and we've lined up a great series of conversations, presentations, and certainly saving time for all of your questions. Please don't hesitate to continue introducing yourselves, where you're at, your interest in black carbon in the chat below. And then please feel free to use the Q&A function. We're going to be tracking questions throughout the presentation, and then hope to reserve a good amount of time to triage as many of those as fast as possible. And obviously, we'll be happy to have follow-up conversations thereafter to further review those in greater detail regarding your projects or the solutions, etc. But without any further ado, let's jump forward, Ryan. What brought us all here together today? So really exciting times. So AethLabs, together with Clarity, have released the new black carbon module, which is built around the MA350, and you're going to hear a lot more about the tech specs of this. As many of you know, we've recently revised the National Ambient Air Quality Standards in the United States for PM 2.5. How does black carbon synergize with this? We know black carbon is an interesting pollutant and challenge, both a short-lived climate pollutant as well as a environmental health consideration. A lot of interest in understanding this, and obviously how these tools can be also useful for improving our PM management around the country. So we're going to talk a lot more about this in a moment, but just jumping forward, I have the pleasure of introducing this wonderful selection of panelists. So first and foremost, jumping off with Jeff Blair. Thank you so much for joining us today, Jeff, President and CEO at AethLabs. Also joined by his colleague, Dr. Drew Hill, who leads data science and applied research with AethLabs. So such a pleasure. Dr. Daniel Mendoza will be jumping in. He's a little double booked with the current conference, but I know he's online and will be jumping in for his session and joining us for the remainder for the Q&A. So thank you very much to Daniel for joining us today. And then finally, our own Chief Technology Officer at Clarity Movement, Paolo Michalizzi, who's been helping and leading the integration Clarity side with AethLabs for this exciting new solution that we're all providing. So without any further ado, I'm going to jump over, hand this off to Paolo to get started, and then we'll be proceeding through a number of presentations. But thank you.
Sean, I think you may be handing it off to me. Is that right?
Nope, just kidding. Handing it off to Drew. Got one job.
All right,
what we're going to say,
Well, good day. Thanks, Sean. As Sean said, my name is Dr. Drew Hill. I head data science and applied research efforts here at AethLabs, and I'm with our founder, CEO, and head of engineering, or chief technical officer, Jeff Blair, to discuss black carbon, its impacts, and the innovations in its measurement to which our company has been committed since 2008. Next slide, please. I'd like to start by acknowledging Clarity for organizing and co-hosting this webinar with us. And thank you, Sean and Paolo, and Dr. Mendoza from the University of Utah. I'd like to acknowledge a number of collaborators with whom we've worked in recent years to establish a good chunk of the content that I'm going to share with you today, or that Jeff and I will share, including folks at the EPA, the French National Institute for Industrial Environment and Risks, ATMO, ADAIR, the Columbia University Climate School, NASA JPL and Addis Ababa University, and the University of Washington, to name a few. Most importantly, and with over 350 registrants from 48 countries shown in this map to the right, I think we've grown by 10 or more so since I put this together early this morning. I'd like to thank you all for engaging with us today, especially those in Europe and Asia competing with dinner and sleep to hear our presentations. All right, on to the presentation. Next slide, please. So this presentation centers around black carbon, a carbonaceous aerosol. Think teeny tiny particles or fine mist that typically account for up to 25% of PM 2.5, which is respirable particulate matter globally. In fact, black carbon is so small it typically measures in at about 100 times smaller than the diameter of a human hair. And black carbon is ultra dark, and you may know it by its common name, soot, which conjures images and thoughts of very black clouds like those shown here in the lower right pictures. Its dramatic ability to absorb light, because it's so dark, as heat, have led to its classification by the United Nations as a superpollutant, an apt moniker given its co-detriment to both climate and health. Next slide, please. A black carbon, or soot, is produced during incomplete combustion, along with a number of other nasty pollutants as well. It's a major component of smoke from wildfires, which research indicates have been increasing in occurrence at twice the expected rate under recent climate change. Twice the expected rate under recent climate change. So the majority of black carbon, however, is produced by human energy consumption. Now, globally, about half of black carbon is emitted during the combustion of fossil fuels and transportation, industry and power consumption, while the other half is emitted during combustion of biomass, which is fuels like wood or other plant materials, agricultural residues, things like that. Now, as you might imagine, contributions vary regionally, as these energy use habits also vary regionally. Now, for example, 60 to 80% of black carbon emissions in Asia and Africa stem from solid fuel use, things like residential cooking, heating, briquette manufacturing industry, stuff like that. While in North America and Europe, about 70% of emissions come from diesel combustion. Now, we've seen a slight decrease in human emissions in recent years. Unfortunately, these gains are being erased by climate-driven increases in wildfire emissions, as you can see in my manually edited graphic here in the upper right. And the impacts are very important. Next slide, please. Now, recent evidence has shown that black carbon is a significant driver of the toxicity of PM 2.5, with health consequences from our nearly ubiquitous exposures between about 3 to 30 times stronger than total PM 2.5 on a per unit mass basis. I recall from previous slides that black carbon typically comprises up to 25% of PM 2.5, meaning that up to 25% of PM 2.5 tends to be tends to be black carbon. And PM 2.5 by itself is responsible for around 6.4 million deaths every year and many, many more incidences of illness. Now, the science of the global disease burden specific to black carbon as the subfraction of PM 2.5 is relatively new. So peer-reviewed estimates of global morbidity and mortality specific to black carbon are scarce. So I don't have the corresponding number, the 6.4 million annually globally. I can't tell you exactly how many from black carbon. To give you an idea, one study estimated about 14,000 black carbon exposure-related deaths in the US alone, a country where concentrations are much lower than many other parts of the world. Now, the key to black carbon's health impact lies in its size and chemistry. The black carbon particulate matter is so small that when inhaled, it can make its way down into the deepest parts of your lungs and bloodstream, or translocate directly into your nervous system, or, if pregnant, into fetal tissues. Now, black carbon is very attractive to nasty chemicals which love to adsorb to its surface, as shown in this graphic here. Commonly identified surface chemicals on black carbon include toxic metals with cardiovascular and neurological effects, sulfates and nitrates that make sulfuric and nitric acid when they react with water vapor in your airways, and other nasty compounds. Kind of an ideal toxics delivery vehicle, right? Next slide, please. Well, black carbon is also a super effective climate warming agent, about 1,000 times greater than carbon dioxide per unit mass, for example. Now, because, well, it's black. Now, black objects absorb heat. Like black asphalt left to bake in the summer sun, black carbon absorbs its heat uniquely well. Absorbs light as heat uniquely well, specifically. Now, this leads to local heating of the air and dimming of sunlight that reduces crop yields. These very small particles often stay suspended in the air for up to 2 weeks, warming the air as they do, but often traveling long distances and settling out as dust onto the Earth's surface, where it can also warm the Earth's surface. And when black carbon settles onto bright surfaces like ice or snow, these particles reduce the Earth's ability to reflect solar heat back into space and increase glacial melt and ice cap shrinkage. Ultimately, due to competing characteristics like its relatively short atmospheric lifetime, black carbon weighs in as the second largest cause of climate change. Now, this short lifetime also makes it an ideal target for reducing climate change. Once you stop emitting it, its direct atmospheric influence is largely gone in under 2 weeks. Now, another reason we call it a super pollutant. Next slide, please. Super pollutants have super trends. In North America, climate-driven wildfires have reduced hard-fought gains in black carbon emissions reductions and increased the toxicity of ambient PM 2.5 per unit mass by increasing the amount of black carbon within it by 2 to 4% per year, every year since 2000. This heat map on the right of the set of heat maps on the right of the US highlights the issue here in the US, where I am, with consequences for health burden and non-attainment days, especially under the new US EPA PM thresholds that Sean mentioned. Now, Europe is also not immune, even to North American wildfires. The satellite image in the lower right, an atmospheric transport model, show transatlantic transport of a Canadian wildfire smoke, and specifically black carbon in 2022. In South Asia and the Himalayas, the superproduction of the super pollutant in the plains results in heavy black carbon settling on Tibetan glaciers upwind to the north, upon which hundreds of millions of people rely for drinking water. This is causing them to melt quickly and to shrink, producing concerns of water scarcity for those same people. Now, these are just a few of the concerning trends in black carbon Now, despite these trends and others like them, there's a stark lack of direct black carbon regulation around the world. Now, experts estimate that the measurement-informed control experts estimate that measurement-informed control in general, not one specific control, could reduce emissions by 80%. It's this context that led our founder, co-founder Jeff Blair, to establish AethLabs in 2008, thereabouts. And I'd like to hand him the microphone to talk a bit more about our history and mission. Jeff, next slide, please.
Thank you, Drew. Well, I'm so thrilled to be here with you all today. Thank you for attending and really thank you for your interest. I'm going to share with you a little background about our company, AethLabs, and the history of our products, microeth products. Our focus here at our company has been to miniaturize aethalometer technology. So hence the name microeth. It's a smaller version of other instrumentation that's been around for quite a while. We've been making equipment with the same capabilities as much larger rack mount instruments, while trying to lower the cost of this instrumentation to make it more accessible. So we want to increase the measurement of this super pollutant and also raise awareness about black carbon and its impacts on health and the environment around the world. So now, through our strategic partnership with Clarity, we are really excited to be able to extend our reach with the integration of our microeth technology into the Clarity Sensing as a Service platform, really catalyzing a transformative approach to addressing particulate matter pollution worldwide. So next slide, please. A little bit about our company. So AethLabs spun out of McGee Scientific, who's the maker of the well-known A33 rack mount aethalometer. We spun out in 2011. My brother Steven and I, it's definitely a family business here. We started AethLabs to focus on smaller, more affordable instruments to help make the technology accessible, really for health research applications. So our main product at the time was the microeth A51, the blue box that you see in the bottom of the screen there, which was really, even to this day, is really the only personal black carbon monitor that's been available. Next slide. So to tell you a little bit about aethalometer technology, there's quite a long history here. The aethalometer was developed at the Berkeley National Laboratory by Tony Hansen and others in the Novicob research group at the Lawrence Berkeley National Lab in the late 70s and early 80s. It started as a real research tool, a device that sampled and measured through a single filter, required quite a bit of intervention by the user. But Hansen later commercialized this instrument in the form that we now think of as the 19-inch rack mount aethalometer, the A33. A few years later in the late 80s, with an automatic tape advance mechanism, which really enabled the technology to be used for unattended long-term monitoring. So my connection to this whole story is I met Tony as a high school intern at LBNL in the late 90s, and I eventually joined McGee Scientific as employee number 1, where I was involved in development of all the technologies and products that are in the company's current portfolio. Next slide. So getting back to the little blue box I mentioned, the microeth A51, you can see London Mayor Sadiq Khan holding it there in one of the images, and actually the mayor also with a Clarity node in the image next to it. So this device, the A51, was released in 2008. And it really put black carbon monitoring in the palm of your hand. So it enabled new research applications. So the instrument was being used on bicycles and balloons and trains and all the science that you could think of for measuring black carbon, all the applications where a rack mount instrument was too large or too heavy or really too expensive, now became feasible. And so now 15 years after the release of the A51, we have a new personal monitor. It's actually another pocket-sized device. This little black box, the AL30, which we're really excited about, but just kind of showing how this technology has kind of come full circle for us as an organization, going back to where I started at McGee Scientific. We did find out that the A51 was actually getting used for all these other applications, not just in, for mobile monitoring, but really for continuous monitoring indoors or for other applications, cook stove monitoring, things like that. And so we knew that there was going to be a need for a monitor that could operate without the need or the requirement of changing the filter strip of that instrument daily. Next slide. So how does the microeth work? So an example that Tony Hansen shared in the past, which I really like, is this. If you imagine taking a white paper napkin and you take a salt shaker from your kitchen table, and you shake some salt onto that napkin. Do you see the salt? The answer is not really, because that salt scatters light, and thus there's no contrast between the salt and the white napkin that is the background. But if you take a pepper shaker and you put some ground pepper on that same napkin, you do see it, because that pepper absorbs light because it's black. And that really is the principle of the instrument. So in this slide, you can see a diagram of the tape cartridge-based AethLabs MA series black carbon monitors, which the Clarity BC module is based on. There's a pump that draws a sample into the instrument, and then we basically filter out particles onto the filter strip there. And then we use a light source, sensitive optical detectors, and we measure the rate of change of optical attenuation that's caused by those particles loading on the filter. So more particles load, the darker the filter gets, and the more light is, the less light is detected by those detectors. So key feature of this instrument is really this tape cartridge. It allows continuous monitoring for up to a year, depending on location and configuration. It's really easy to exchange. The patented dual spot technology here is used to compensate the measurement based on different aerosol compositions. And so it's a key feature of our MA series products and the Clarity BC1 module. And that's a technology that we share with the A33 instrument as well. Next slide, please. So I'm not going to get into the dual spot technology into much detail, but here you can kind of see an example of uncompensated data at high loadings, where the black trace in these two charts, where the uncorrected data is perhaps reduced over time from the real value. And this was kind of a symptom of the aethalometer in the early days, until this technology came about close to a decade ago. And so what we basically do is measure this effect, and the kind of gray trace at in the bottom chart is the compensated data that is built out of the dual spot technology. It's created from the dual spot technology. Next slide. So some basic specifications. We really tried to take all the key features of the rack mount instrument and squish it down into a very small form factor, and to make the measurement more accessible. So on the left, we have the MA350. You can see the size and the weight. One key feature is, it has built-in battery for multiple days of operation, the dual spot measurement, and source apportionment, which Drew's going to be talking about a little bit more as well. Next slide. So just to touch on source apportionment, if you look at these data here on the right, you can see there's a black trace. That's our kind of black carbon measurement, our total black carbon measurement. And then the middle trace, the kind of golden trace, is the wood smoke measurement or biomass burning measurement. And then the blue trace on the bottom is from traffic emissions, think of diesel exhaust, et cetera. So you can see we're starting to tease out these different patterns in the data based off of the multiple wavelength measurement that we make in the instrument. Next slide, please. So Drew's going to talk a little bit shortly here about additional projects and campaigns and validations of our technology that's also in the Clarity BC module. But one of the earliest validations here was one carried out by the EPA. It's not an endorsement, but this is a poster that was presented by Dr. Emmer Holder. I believe I've seen Brandon, who was also involved in this project. I think I saw Brandon join this webinar a little while ago. But anyway, this is basically using the MA350 for a number of different applications, high concentrations, burn pits, wood burning, fireplaces, things like that for residential heating. And if we go to the next slide, the results of that work really kind of showed that the dual spot correction technology was working effectively in the MA350, resulting in a significant reduction of up to 60% of the loading effects that are sometimes present in different aerosols. And that the concentrations measured by the instrument was also consistent with that of the AA33, ensuring uniformity and reliability across instruments. And then third, that there's superior performance in some applications. So the MA350, because of its low flow rate, that in some of these source and ambient conditions, that the instrument performed better than other instruments just due to its lower flow rate and lower rate of loading. So really strong performance in terms of those comparisons. And with that, I'm going to turn it back to Drew to kind of get into some more details. And thank you very much.
Great. Thanks, Jeff. Next slide, please, Sean. Well, since our first early validations, our dual spot microethanometers have been used widely around the world. Now, as a somewhat quantitative example of this, a very explicit search of the scientific literature on Google Scholar revealed about 131 results, 593 if we expand the search slightly. And this is a fairly, well, to me anyway, impressive number. Pat ourselves on the back, I guess. But this includes numerous performance evaluations against other best-in-class instrumentation with overwhelmingly positive results. Shown here are just a few examples I pulled last night, including a collaborative effort that Dr. Mendoza will discuss in more detail to the far right here. Next slide, please. Some other charismatic work with our microethanometers includes the identification of BC exposures in New York City from California wildfires, quantification of bicycle commuter exposures, revealing ultra-high BC PM2.5 ratios in the densely populated capital city of Ethiopia through collaboration with Maya Satellite Project and of NASA JPL and the Italian Space Agency. Thanks, Sina and Araya, who are on the call today. Characterization of BC exposures in US cities and tribal areas, measurements of to validate air purifier performance in schools, quantification of cognitive effects from BC exposures, drone-based measurements for more safely assessing near roadway pollutions, and many others. I won't go on too much about that, but next slide, please. One particular application I'm quite interested to talk about, and that Jeff mentioned earlier on, is source apportionment in real time. We do this by leveraging multi-wavelength measurements, as Jeff mentioned. I won't get into the weeds, but generally a physics principle called Beer's law, in tandem with the differential coloration of the specific aerosols emitted at the same time as black carbon combustion, relative to, or from fossil fuels relative to those same pollutants in this carbonaceous aerosol mix produced by biomass combustion, allow us to use peer-reviewed equations to estimate BC mass concentration specifically from fossil fuel combustion, separately from biomass in real time. Given the previously discussed regional heterogeneity and source contributions, and the continuous insights this feature provides, we believe can help policymakers identify the most critical sectors for efficiently and effectively reducing local black carbon emissions, health effects, and climate impacts. Next slide, please. Now, I'm conscientious of time here, so I don't want to go too much into more details, save Sean some headache and heartache here. But this feature of source apportionment was long vetted, in part through a 2-year campaign by French national scientists at INERIS and Atmo Auvergne Alps. It's a particularly complex black carbon landscape in France, with multiple key sectors, regional pollutant transport, and mountain orographic effects, like chimney effects up the mountainsides, stuff like that. They also have a uniquely vast national black carbon monitoring network, an example to be emulated, absolutely. Now, these scientists co-located our instrument, the AethLabs MA350, alongside another best-in-class black carbon monitor, the McGee Scientific A33 that Jeff mentioned, and probably had some part in developing early technology for. Ultimately, finding strong performance of this instrument and accepting the instrument for use at its stations. Next slide, please. So these are just example data from one of those co-locations in Lyon. Suffice it to say that close overlap on the left of our instrument, the blue trace, and the other instrument, the red trace, with black carbon on the top and black carbon specific from biomass burning. So top is total black carbon, bottom is that specific source apportioned rate, as well as close to one slope and strong overlap on the right suggest good agreement and performance. Next slide, please. I'd like to close by reiterating that black carbon is soot. It makes up a critical portion of PM2.5, is responsible for substantial death and illness in both the global north and south, is the second leading cause of global climate change, and is critically lacking in direct regulation. If you take away from this talk any notion of AethLabs, I hope it's that AethLabs works and has worked for over 15 years to inform health and climate action through innovation in the portable, reliable, and affordable best-in-class measurement of black carbon. You can flip through the next 2 slides, which are just my works cited, please, and on to the last slide, which is just a thank you. Much appreciated. Oh, and this was an image, a video showing the wildfire smoke from Canadian wildfires coming down and hitting some of the most densely populated parts of the U.S., leading to exposures. But instead, I've described it for you. So thank you. I'll hand it back to Sean.
Perfect. Thank you so much, Drew. Well, really fantastic background, and thank you so much for providing such valuable context on black carbon generally. Going to jump over now at this point to Professor Daniel Mendoza, who's joined us. And Daniel, if you're here with us and pop the camera on, I know you're jumping out of a conference, give you a second here. But yeah, very much looking forward to hearing about some of the work going on in the University of Utah. It's been a great collaborator working together with AethLabs, and certainly a lot more exciting research moving forward here as well. And Daniel, as soon as you can have mute, perfect.
Oh, online, can you hear me?
Yep. Over to you.
Great. Well, thanks. Good morning. As Sean just mentioned, at an air quality conference actually where we're discussing PM10 apportionment, and so it was a very relevant topic. So just kind of bouncing back and forth between here and the conference itself. I'd like to start off with this image. I always like to have a neat sort of front slide here. And this is this, I guess you can't quite tell what it is unless I tell you the date, which is middle to late May of last year. So many of us, essentially the whole US, felt to some degree the impact of the wildfires taking place in Canada. And I took this picture as I was riding my bike. You can see it's a bike path there on the lower right. And you can actually see a little bit to the bottom left, the truck. It's a diesel truck, so this kind of really captures the essence of carbon, right? Those are the two primary sources, which is biomass burning, in this case, the wildfire, and then also the trucks or diesel emissions there. So let's go to the next slide, please. So in terms of background, these are all, I think we just want to click through them one by one. So as has probably already been mentioned, black carbon is a health-related pollutant. It's also a strong climate change driver. There are sparse observations. There's many difficulties in terms of observing. The observation network is not as wide as for other pollutants. There is some involved maintenance as well. That the fact that there are things involved and needs calibration, etc. Is also traditionally costly pollutant to monitor for multiple reasons, especially the maintenance. And there are environmental and social justice implications associated with black carbon. So not only, for example, as I just showed in the picture prior to the slide, not only do we have to be considering places that have high traffic, for example, high potential for wildfires, but also if we think about countries in developing nations where we're thinking about a solid fuel that is consumed on a regular basis at the heating and a cooking source. On the next slide, please. Let's like to start off again with another eye-catching image here. And this is the air filter change day. So this is for my home actually. And I'm going to be bouncing back and forth between particulate matter and black carbon as well. So just bear with me because again, black carbon is a subset of particulate matter. So one thing that I always like to bring up is I take great care of the air pollution and the air quality that I breathe in my home. I have asthma, so for me that's something that's a substantial concern. And so when I look at the filters here, thinking if this wasn't being caught by the filters, then that's going into my lungs. And so this takes about 2 months or so for my filters to go from clean to dirty. And again, some of you may be familiar, Utah has some air quality challenges, primarily during the wintertime or at wintertime inversions, where air gets trapped and it doesn't move around as much. Next, please. So a project that I've worked with through Jeff and a colleague at West Texas A&M, we wanted to do a long-term comparison between the AethLabs, the MA350, and then the McGee A33, which is what's widely used in regulatory monitoring stations. So this is a paper that just came out at the end of January. Next slide, please. And when we, first of all, we looked at multiple time scales. So we look at the daily average. What we're ultimately interested, of course, there are multiple channels that are used to measure concentrations, but ultimately what we generally want to look at, particularly for health studies, are biomass and fossil fuel concentrations. And as you can see, the MA350 and A33, they match very well at the daily scale. But if we also look at the hourly scale on the next slide, we see that the matching is also very good. It seems to deviate a little bit in biomass, and part of that is due to there's just lower concentrations overall. So small spikes read by an instrument or the other instrument, they can change this a little bit. But by and large, fossil fuel is pretty much spot on. And biomass is, again, has a little bit of variability, but it's nothing to really be concerned about. When we look at the next slide, we want to really consider what are the implications. So, first of all, the concept of data democratization is ensuring that communities are able to really have access to data. And that really begins with having more sensors and having accessibility issues that get addressed. And when we go to the next point, we want to really develop that. I think that it's very clear that, for example, very similar to PM 2.5, black carbon concentrations can vary substantially, particularly near concentrated sources such as roadways. Then when we want to look at the diurnal pattern, so because of areas that are, for example, very close to highways that have a lot of that are very regular diurnal patterns, meaning morning rush hour, afternoon rush hour, we can start to establish some of these patterns, which can then help us develop some of the arguments towards how can we actually detect populations, which are the public health applications. Can we go to the next point, please? We also would want to think about potential early warning systems. So if we have, for example, here in Utah, the majority of our wildfires come from western states, the coastal states. And so if we start to see, for example, a wildfire plume hitting communities that are, say, an hour away, then we can start to warn communities that are downwind, and then we can start to reduce some of the potential exposure. And we can also help develop environmental refuge. So we could be thinking about what are some solutions. So not only being able to warn people, but how can we provide some help? Next slide, please. So currently we have a very dense observation network. There's some of the Division of Air Quality, so regulatory agencies monitoring sites. So have some stationary sites operated by the University of Utah, and we also have air quality sensors that are installed on top of the light rail. Next slide. What we also did was we started to place air quality sensors on top of electric buses, and these are our measurements. We currently have 21 million observations, and again, these are reported every minute. So this is for PM 2.5 at Bluestone, and ideally we would like to move forward and see if we can add black carbon to a suite of observed pollutants. If we go to the next slide. So there's some of the soon to be released studies using the MA350. It's got some observations inside and outside the University of Utah, some buildings, strategy, building infiltration, similar studies done at the Salt Lake City School District. We're also looking at rural schools because rural communities tend to be understudied as well as tribal communities. We've seen the impacts on some firework events. And then, as I mentioned, the wildfire in 2023, as well as the 2021-2022 wildfire season, which was currently active. I think that might be my last slide. So thank you for your time.
Wonderful. Thank you so much, Daniel. Really appreciate the context, the great examples here, talking about, again, perfect examples of how we can use this data and the new solutions around that to effectively better inform some of the challenges that we're dealing with as communities and societies, but likewise some of the potential solutions. All right, and then next slide, without any further ado, we'll move forward to my colleague, Paulo. So Paulo, I'll let you take it away from here. Thanks.
Thank you, Sean, and thanks everyone for joining today. So today I'm going to be talking about how black carbon monitoring fits into Clarity's platform. For those of you that are less familiar with Clarity, our mission is to empower the world to reduce air pollution. So we work with organizations, both public and private, and we enable them to monitor air quality at an unprecedented spatial and temporal resolution. How we do that, next slide, please, is with our sensing as a service, which is comprised of monitoring hardware, cloud software, and remote air quality expert support. Now, to talk about how black carbon fits in all of this, I would like to spend some time talking about our monitoring hardware. So the Clarity Node S is an IoT device. It's solar powered. It connects to the cellular network. So it's independent on existing infrastructure. You don't need a power plug. You don't need a Wi-Fi network outdoors. So you can deploy it easily anywhere. It's ruggedized and it's made to operate reliable outdoors in a harsh environment for years. And it measures accurately PM and NO2. And most relevantly to this talk, we consider this the key building block of our platform because its measurement capabilities can be extended with the use of add-on modules. And what we did is we partnered with AethLabs to customize the MA350 to become Clarity Black Carbon module. So one question that could come to mind is what are the benefits of monitoring black carbon through the Clarity Sensing as a Service platform rather than with a standalone instrument? And I'm going to talk about 4 benefits. The first is ease of deployment. So what we did with AethLabs, a big part of the work was to work together to ruggedize, weatherproof, and insulate the MA350 so that it can be deployed outdoor in a stationary monitoring setting and operate reliably for a prolonged amount of time in harsh environments. So you can imagine walking up to a pole, you mount the black carbon module, you mount a Clarity Node S right next to it, and then you plug a single cable from one to the other, and this takes care of all the configuration needed. And sometimes it can be daunting to configure these analytical instruments, so this is streamlined. And at this point, so luckily the onboard little solar panel of the Clarity Node S is not enough to satisfy the power requirements of the black carbon module. So you can either plug the Node S into power outlet with the provided power adapter, or we also provide an external solar system that is larger, so you can also connect to it. And this is the second cable, so 2 connections, and you can have your black carbon module deployed anywhere. So it relies on the external solar system for power and on Node S cellular for communication. So imagine no need for a container-sized shelter with air conditioning, a laptop with software installed. It's really easy to deploy compared to alternatives today. And this is ease of deployment. The second benefit is seamless data access. So the black carbon module communicates through the Clarity Node S to the Clarity Cloud. And this means that you can see in real time black carbon measurements streaming through our Clarity dashboard. So not only you can see real-time mass concentration measurements, but you can also see real-time source apportionment estimation. So you can see the percentage of black carbon that comes from fossil fuel burning versus the percentage that comes from biomass burning, as we heard during this presentation. And then you can start doing already some analytics within the dashboard. You can compare black carbon concentration across different sites, or for the same site, you can compare black carbon concentration with other measurement parameters. And if needed, it's very easy to integrate with your existing systems through the Clarity API. Next benefit I want to talk about is best-in-class data quality. So maybe this is a bit repetitive at this point, but we at Clarity, we really value accuracy, and we believe that indicative monitoring is exciting. It opens up a lot of opportunities and new applications, but it has to be founded on a solid base of reliable and accurate data if you want to turn this data into meaningful and impactful action. So since the beginning of our collaboration with AethLabs, we focused on accuracy. And here I show some of the work we've done in the next slide. So this is a comparison that we did ourselves between our black carbon module and AE33 that we operate ourselves in Berkeley in our lab. And you can see that there is very good agreement both on the time series chart and on the scatter plot, with R square above 0.9 and a very low root mean square error of 145 nanogram per meter cube. And this similar results were obtained as we started testing this in different environments. So you can see in the next slide results in Denver, Colorado, and also similarly in Florida. There we go. So very similar results in very different environments, which is what you want to see. Now, for the fourth, last but not least benefit is co-located PM2.5 and black carbon measurements. So this is very interesting. And let me give you an example of some work we've done in Berkeley that shows the potential for this. So the first thing you can do with the black carbon module is you can measure black carbon concentration over time, right? So this is already useful, valuable. So you can plot black carbon concentration. This is an example for a few days in Berkeley. And you can already start making some observation about the concentration levels and put maybe their health impact. But then as you start seeing this type of chart, this already start getting questions. For example, what are those spikes on the left that seem short-lived? And then what are those recurring peaks in the mornings to the right? So to go a step toward the answer, you can add PM2.5 measurements to the chart. And here we can already make an observation, which is that PM2.5 concentration and black carbon concentration correlate. So you can see that they go up and down at the same time. Their shape matches. And this drives the conclusion that the air quality in Berkeley in this period is mostly impacted by combustion emissions in terms of PM2.5. And now you can do even more if you add to the mix the source apportionment estimates. So, okay, PM2.5 pollution is driven by combustion, but combustion of what? So you can see that as the fossil fuel and biomass concentration cross, you can see which one contributes more. So you can see that those short-lived peaks to the left are mainly coming from biomass burning, while the morning peaks to the right, they are from fossil fuel combustion. And you can start making conclusions here. Next slide, please. So our hypothesis was that these spikes to the left are caused by wildfire smoke, while the morning peaks are caused by commuter traffic. And in fact, this was confirmed, as we can see here in the next slide, from an article of the New York Times that talked about how air quality in the Bay Area was impacted by wildfire smoke from Oregon in exactly that day. So this is already impressive with just a few days of data of co-located PM2.5 and black carbon data. So now a little sneak peek in what's coming next, we're actually working on enhancing the Node.js for multi-module support so that you can, with the addition of a wind module, you can also add wind speed and direction to this. So you can go even further with your analysis. And now to wrap up, we talked about 4 main benefits: ease of deployment, seamless data access, best-in-class data quality, and collocated PM2.5 and black carbon measurements. Now, the next slide has some contact information in case you want to get in touch and discuss your monitoring needs or the ideas you have to leverage this exciting technology. And I'll send it over to Sean for continuing with the Q&A section.
Fantastic. Thank you, Paulo. Super excited. So please, yes, there's going to be, conscious of time here, we have a lot of great questions to answer, and we're going to have a lot of time to discuss those both during the webinar, well, mostly after the webinar at this point. But did want to quickly ask the panelists if there's any of the questions that you're particularly interested in answering, please do flag them now. Otherwise, I will start at the top, proceed through a few of the different questions here. But again, big thank you to our panelists so far. All right. So I actually have one here from Sairam that I think is quite an interesting topic to start off with, which is how can BC be accurately included in air quality index measurements to provide a comprehensive assessment of air pollution? Or would including black carbon bring in additional confusion to targets already based in PM levels and concentrations? Who'd be interested in answering that? I think it's a fascinating question from the challenges that indices present us in the air quality management space. All right, Drew.
Just take a quick stab. I mean, I haven't really thought about this. This isn't one of our question plans, unfortunately. I think the air quality index has substantial benefits and also substantial difficulties associated with it, right? One of the difficulties is the nonlinearity, I guess, in a way, of the health impact of exposure to PM2.5 on health outcomes that's been observed. You know, the really low exposure is actually the increment from going from no exposure to a tiny bit of exposure is much more of a health impact than going from a really high exposure to a slightly even higher exposure, or like the same amount of higher exposure. So that's been pretty interesting. I think that perhaps delineating the nonlinearity here, or at least shedding some light on perhaps what's contributing to this nonlinearity in terms of content. You know, we do know that PM2.5 mass is a very good indicator for health outcomes, but we know that there are some better ones, like black carbon, for example. You know, certain types of PM2.5, like sea salt, have much different and lower or negligible effects on health than, you know, say, direct lead dust at PM2.5, you know, for example. So black carbon, if we can measure it accurately in real time, as we know can, then we can leverage the existing epidemiology to come up with specific thresholds. We could potentially have, you know, either its own indicator. It would have to become a criterion air pollutant, I think, to really get that sort of attention, or it could be a fractionation of a ratio. You know, how toxic is the PM that you're being exposed to, as assessed by the percentage of PM2.5 that can be attributed to black carbon specifically, since we know that black carbon is some of the nastiest type of PM2.5 that exists in ambient air. So I kind of just bloviated. I'm not sure I have an exact answer, but I think, you know, there are 3 different approaches I could see happening: direct BC, or black carbon, AQI, a ratio-specific AQI, or something in the algorithm in the background that helps inform the PM2.5 AQI that maybe isn't directly called out immediately in the colors, but maybe helps identify the colors. So
awesome.
Just a thought.
Wonderful. Thank you, Drew. No, I really appreciate your insights on that. I mean, AQI is a complicated topic, and particularly around the world in many ways. I'm going to jump forward another question here from Roger Van Uden, and thank you. So the BC module is a big box. What's inside? Is there heating, temperature differences, winter, summer? You know, the Node S traditionally has an end of life, maybe 40 months. What about the BC module? Instrument in the module based on what? Paulo, you can see this question here, so I'll let you start answering instead of me just blabbing here for a sec. So.
All right, thank you, Sean. So what's inside the box, right? So inside the box, there is a MA350 from AethLabs, the instrument that we saw being presented by Jeff earlier on, which is best in class and has been tested in peer-reviewed studies across the globe, I would say. So it's a very solid foundation. And in terms of temperature differences, winter, summer, this is exactly the main part of the work we did together for making this portable instrument into something that can be deployed outdoors and can operate reliably in a stationary monitoring setup. So we actually put a lot of attention on testing the effect of especially rate of change of temperature on the baseline stability of the instrument. And I have to say that we did a good job with installation, and we have a sun radiation shield that we added on it so that we can really minimize the effects of changes of temperature on the accuracy. And I think this is, as I was saying, is one of the main benefits of working with this configuration. In terms of end of life, so we recommend to send the instrument back for servicing every 2 years, right? So that's taken care by the servicing, but actually that's the beauty of our business model of sensing as a service, which is that we charge customers a yearly fee per monitoring site. That of course changes depending on how you instrument the site and what you want to monitor. But then at that point, the hardware is part of your sensing as a service fee, right? So if there is the need for replacement, we will just substitute with a new instrument. So you can continue your monitoring campaign long term. I see tapes. How long will it work unattended, right? So that's a great question. So maybe Jeff can answer better than me, but what I can say is that, of course, it depends on the concentrations, but we are targeting one intervention every 4 to 6 months. But Jeff, please take it from me on this one.
Sure. Thanks, Paulo. So it's a great question. Thanks, Roger. So it is quite variable, just like black carbon. That's why we have to measure it. We can't really use a model to predict it. Depending on concentrations, we have had some MA350 instruments out in the field where they've operated for up to a year on a single filter cartridge. And that's kind of in some urban near roadway type environment. But I think for the BC module, the Clarity BC module, that we are building in a number of filter cartridges per year as part of the service agreement. And I think there are options that are quite affordable in terms of increasing the number of filter cartridges depending on location. So you can basically get started. And if you're finding out that consumption is higher than expected or application changes, perhaps you get closer to a source, or maybe you're doing fence line monitoring, you can upgrade your service plan to include more cartridges. I hope that answers the question.
Wonderful. Thank you so much, Jeff. Thank you, Paulo. So I'm going to answer a few of these questions or requests that we answer a couple here. There's regarding the wavelengths. So I see a question regarding, are the 5 wavelengths of the MA350 with which this instrument is built included within the dashboard? Can we access all of the wavelength data? And then also, what are the different wavelengths provided by the instrument's measurements? And then discussion a little bit about the separation of those. So the BCFF versus the BCBB, et cetera. So I assume anybody want to jump in on that one there?
I can talk about the dashboard, and then I can probably send it over to Jeff for the rest. So in terms of dashboard, so for data visualization, we prioritize the total black carbon concentration and the source apportioned figures. So the percentage of it that is contributed by biomass burning and by fossil fuel burning. But one of our philosophies at Clarity is to always make raw data available, right? So all the raw data coming from the instrument are available via our API. So if you want to really dig deeper and do work, advanced work with all the raw wavelength data, you can get it through the API. Whenever there is a calibration or modification done on the cloud, we have full traceability of that, and we always preserve the raw data.
Perfect. Thanks, Paulo. And then Jeff, did you want to mention the specific wavelengths that were included?
Yeah, so the 5 wavelengths used in the MA series instruments, we use 880 nanometers in the infrared for the kind of typical black carbon measurement. We also have 625 nanometers red, 528 nanometers green, 470 which is blue, and 375 nanometers in the ultraviolet. We use the 880 nanometer infrared and the 470 nanometer blue channel for the aethalometer source apportionment model that's built into the instrument and provides the data product for the biomass burning and traffic source apportionment.
Great, thank you. Now, realizing that we are just about at time, I'll take one more minute just to circle up any final questions, or maybe offer to the panelists. Is there anything that you would take away, or the questions regarding black carbon that you're particularly interested to see explored? Where do you see the science going? What do you see as the biggest exciting opportunities for this instrument and for the field of black carbon measurements moving forward? And maybe I'll start with you, Drew.
Oh, well, you'll have to talk. I have some thoughts on this. So I think one of the most exciting parts to me of the partnership with Clarity is the network of instruments you guys have out there and you've already cultivated. And so I think that being able to instantaneously, plug and play, it just works kind of black carbon functionality is huge. And, as we discussed, or as I discussed in my presentation, the state of regulation for direct black carbon mitigation is dismal, if even existent. And part of that is because the measurement state, or the state of measurement globally and domestically for us in the US is pretty poor as well. So being able to increase the potential, breadth and scope of black carbon measurement around the world really excites me. And why does it excite me? Well, we really need to start targeting this directly. We've been relying so far on the fact that black carbon is a co-pollutant with a ton of other pollutants. Basically, anytime you have incomplete combustion that produce black carbon, you're also producing general PM 2.5, gases, stuff like that that's being regulated right now. And so as you decrease and regulate those, you do decrease black carbon. But it's not a one-to-one, and it's not necessarily targeting the key issue here for climate, at least as the second largest contributor to climate change, and as one of the most important health-related constituents of PM 2.5. So being able to get more measurements out there, to do more epidemiology with, to create more compelling legislation with, I think that really excites me, as well as being able to understand in real time the sort of increased or decreased toxicity of the PM 2.5 measurements you're getting. So
fantastic.
Yeah.
Thanks, Drew. How about you, Jeff?
Yeah, I was thinking about this a little bit this morning. I think one of the things that's most exciting to me is and not to be making kind of a marketing pitch here to everyone, but I really feel like this collaboration with Clarity is especially exciting to me because for the past 10 years of my career, and I've been doing black carbon measurement, for nearly 25 years. It's crazy to say that, but we've really been wanting to try to find a way to have impact and building networks of instruments and sensors and having spatiotemporal resolution to start answering some of those real questions around individual exposures, health effects, trying to have some real impact on environmental justice in communities that are disproportionately exposed to not just particulate matter, obviously, but just pollution in general, and are having real health effects, kids at early ages being impacted. I'm excited to see technology move in this direction to kind of have an impact on the health of individuals. And so I am excited by this partnership with Clarity because I think we are going to be able to reach a lot of communities that, as a small business, we have been unable to do so far. So thanks for asking that question.
Thank you, Jeff. And Paulo.
All right, and I really agree both with Drew and Jeff. And for my answer, I'd like to quote one of the questions I see that the audience submitted. Actually, it's a question from our friend Collins. So he says, black carbon is not regulated. How do we make a case for its monitoring, specifically in regions where this data will be more desirable, including EJ communities, right? And I think this is exactly the point. That's why we funded Clarity, right? It's to enable monitoring of pollutants such that we can have action based on data. If you cannot measure it, you cannot fix it. So we want to, of course, this is just the first step in a big chain of things that need to happen to get impact. But by leveraging novel technology, making it easy to install, making it possible to deploy anywhere, streamlining the access to data, making it intuitive, we really want to slowly tear down these barriers and make it accessible. And that's kind of our contribution in making our case for monitoring of black carbon and also PM2.5 and O2 ozone where it's needed, right? So that's my answer.
Great, thank you, Paulo. Well, I want to thank everybody again. I do apologize as I'm sitting looking at over 25 great questions we haven't had time to answer today. It's not that your questions aren't appreciated. It's simply that we're trying to, frankly, a little out of time. So please, please, please do reach out to us directly, and we'd be happy to discuss all these fantastic questions directly with you as well to make sure we can have a further conversation and not to abbreviate an answer to those beyond what they are. So with that, I just want to thank everyone once again, including our panelists, Paulo, Jeff, Drew, Daniel, so much. I also want to give a shout out to Ryan, our mastermind behind the scenes that did a fantastic job, as always, coordinating and orchestrating this whole thing. But really excited again for all of you participating in your interest in black carbon. Please don't hesitate to get in touch with us. We're pretty easy to get a hold of, and I'm very much looking forward to continued conversations with hundreds of you very soon. So looking forward to addressing this great challenge. And until then, you all have a great day. So cheers.
Thank you so much. Bye.
Thanks, everyone. Really appreciate it. Take care.